Okay, so welcome to the fourth lecture. So we would continue with our discussion about divide and conquer algorithms. Okay, and today we are going to talk about a fairly non-trivial problem. So last time we were sort of warming up in some sense, right? So we saw multiplication, we also saw inversion counting and Strassen matrix multiplication. But today we are going to talk about something quite quite nice, but at the same time it might take a bit of a time to grasp the entire thing. But let's see how far we can do. Okay, so what is the problem we are talking about today? So the problem is, let's say in a two-dimensional plane, I'm given a bunch of points. Okay, so when I'm talking about two-dimensional plane, I mean that every point is specified by two coordinates, one the x coordinate and the other the y coordinate. And I'm also given a distance function. And we all know that since it's the Euclidean plane, so I'm talking here about the Euclidean distance between 2 points, which is given by this expression. Okay, so I hope all of us are aware of that. And now the goal is simply to return the pair of points which are closest to each other in this two-dimensional plane. Okay, as simple as that. Right. So why do we care about this problem? So first of all, I think this is probably the first problem that you are seeing definitely in this course, which belongs to this broader area of algorithms called computational geometry. So computational geometry. Okay, and it's a very prolific area in algorithms, and especially computational geometry algorithms finds a lot of application in areas like robotics or computer vision, and even in a broader sense in data science. Okay, so which is why it's extremely important that we are able to solve these problems very fast. Yeah. Okay, so today we're talking about this very basic fundamental geometric problem of finding the closest pair of points among a given set of points. Okay, so I'm going to make one assumption throughout this lecture, and this is again, I often do these things just to keep the lecture simple, but the algorithms themselves, they completely work exactly in the same way, even if I remove these assumptions. Okay, so the assumption that I'm going to make is that every point has a distinct x or y coordinate. Okay, so no two points have the same x coordinate or the same y coordinate. And now, of course, this is not a very general assumption. You might have a set of points where this assumption is not valid, but then I claim that there is actually a way to what I call perturbing the instance a little bit. So what is perturbation? Perturbation is simply that you change all the x and y coordinates by a tiny amount so that now they all become distinct. And now if you run your closest pair finding algorithm on this perturbed instance, then it will return the correct answer. It will essentially return the same answer as the original set of points. Now, how we do the perturbation, I'm not going into that. There are several ways of doing it, but just for simplicity, assume that each one has distinct x and y coordinates. Okay, this is not going to affect the algorithm itself, but some part of the analysis will actually use this fact. Okay. Okay. So everyone clear about the problem definition? Good. And okay, so of course now we know that there is a naive algorithm to solve this problem, right? We can easily solve this problem if we are allowed order n square of time or theta n squared time. So you can just check every pair of points and you can return the closest one. So clearly that's not what we are doing here. We want to design a faster algorithm. So in particular, we are going to see an algorithm which takes order n log n time. Okay, good. So let's even going into the actual problem. Let's just think about the problem a little bit. Okay, so suppose I give you an easier problem. Suppose the problem is completely in one dimension. Okay, so what do I mean by that? That every point essentially has the same y coordinate, right? So it's like, think about a line which is parallel to the x-axis, and every point lies on this line. So how will you solve this problem? How are you going to find the closest pair of points among this bunch of points if they are all placed on a single line? So how do you solve this problem in order n log n time is the question. Okay, so right, so there is so already some people have answered. So what you can do here is right. Okay, so the point is we can sort the points. So sort the points according to x-axis or x-coordinate, and then check every adjacent pair. Okay, so right, so the point is, if I sort the points, then I know that whatever the closest pair is, they have to be adjacent points in this ordering, right? So remember, the initial set of points that I'm given can be unsorted. You are just given a set of points. So the x coordinates, the array which is given to you, the x coordinates might be everywhere. But then, I know how to sort in order n log n time. So I just sort and I check every adjacent pair. Yeah. And I know that I will end up catching the closest pair. Okay. So one important thing to note, although this seems like a trivial case to solve, this is not trivial, by the way. This is trivial given the fact that now we are mature enough to know that sorting n numbers can be performed in n log n time. That is why this problem looks trivial now, but not at all trivial. You need a good algorithm for sorting at the end of the day, even to solve the one-dimensional case. But anyway, but one message that we should take forward is that somehow, why is sorting helping us? So can anyone tell me what is the principle behind this sorting? Okay, so what is the principle that we are able to use in a general sense after sorting these points? What is it that, so remember, I'm comparing against this naive algorithm which checks every pair of points. Okay, right. So divide and conquer, of course, is the sorting algorithm, but I'm asking a slightly different question here. All I'm asking is, uh, why does step 2 work after step 1? So in the sense that, what is it that sorting is actually reducing? So why does sorting reduce the complexity of finding the closest pair from order n square to order n log n? What is the basic principle that is going on here? Very good. So the number of comparisons is reducing because of sorting. Extremely important. So please remember this, because this is exactly the principle that we are going to utilize um, when we'll talk about the two-dimensional case. Okay. So for every point, all I'm doing is, yeah, so I will repeat the question. So all I'm asking is, we know that this problem can be solved in order n squared time, very naively. You can compare every pair of points. But after sorting, so I spent some amount in sorting these points, which is n log n. But now this is giving me a benefit. I have an ordering of my point, right? But why is this ordering really helping me to find the closest pair? At the end of the day, sorting is not my goal, right? Finding the adjacent pair or finding the closest pair is my goal. So why is it helping me? So in some sense, it is reducing the amount of search that I have to do. For every point, now I just compare it with the very next point in the sorted order. I do not need to compare it with every other point in the set. Okay, so this is kind of, so it seems trivial for the 1D case, but you will see that this is actually the driving principle of our algorithm. So note that sorting reduces number of comparisons that we need to do. All right. Okay. So please keep this in mind. Okay. Now let's go into the 2D case, right? Okay. So now one immediate thing that might come to our mind, or some idea, this idea might actually come to our mind that, okay, what if so I have two coordinates now. The point is I am now in 2 dimensions. So I have two coordinates now. So clearly I don't know which coordinate to sort by, right? If I try to use the previous idea, so let's just sort by both the coordinates. That does not cost us too much extra, right? I just need to perform two sorting algorithms, which is 2 times n log n, or it just increases by a factor of 2. But the point is this idea going to work? If I sort by XY coordinates and then just try to go over the list independently, do you think this idea is going to work? Yeah, clearly this idea is not going to work, right? So we can create a very simple example. So suppose that I have a point A here, right? And I have a point B, which are very close as far as the X coordinate is concerned, but they are very far away as far as the Y coordinate is concerned. This can happen, right? Whereas, let's say the actual closest pair of points is something like this. Okay, so this is A prime and this is B prime. Now, for example, if you sort according to the X coordinates, what is going to happen? Well, A prime and B prime are not going to be next to each other in the sorted order, clearly. Yeah, because A and B will come in between them. And then you will not get the correct answer. So this idea of checking only the adjacent number does not work anymore. So all the advantage that we were getting in the 1D case by sorting the points along the line, that is completely lost if I naively try to sort of import that idea. Okay, so this is very clear. And a similar example you can create for the other direction as well. So if you sort according to Y coordinate, you can again make A and B, which are far apart as far as the X coordinate is concerned, and then you can do this thing. Okay, so clearly we need new ideas. So of course we are going to use divide and conquer algorithm. So let's at least see how to divide the problem, right? So what is the most natural way to divide the problem up? So first of all, what we will do, and this is a general principle that you should keep in mind, that whenever we are looking for n log n kind of algorithms, sorting is a routine that comes for free to us, right? Because we know how to do sorting in n log n. So whenever possible, just sort everything. Yeah, because somehow we don't know whether we will use the sorted ordering or not, but it doesn't harm to actually sort the elements that are given to you. Often it actually helps. So what I'm trying to say here is that often we will assume that we are just sorting things and we are just spending another n log n time in this procedure. So in the same vein, what we are doing here is we are again sorting the point set according to the X coordinate and the Y coordinate separately. And I'm calling these two different lists, Px and Py. Yeah, remember both Px and Py are the same set of points. Yeah, and we are it's only that Px is the same set of points sorted in X coordinate, and Py is a set of points which is sorted according to the Y coordinate. Okay, good. Now, how are we going to divide the set of points? So remember, I want to divide the set of points in such a way that the two divisions are roughly of equal size. Okay, so a natural idea is to remember, now I have this sorted list Px. So I find the median point according to the list Px. How does that look in the picture? What it essentially means is I am drawing a line somewhere in the middle of this picture, somewhere here. Okay. Yeah, I did not draw it very well. It should coincide with one of the points. So let's say something like that. Okay. So this is what I'm doing. Okay, so this is a divide step. I'm just dividing the set of points according to the list that I have sorted by the x coordinates. Yeah. So my left half now I call Q, and the right half I call R. Okay. And both of them contain roughly the same number of points, maybe, up to floors and ceilings. Of course, if again n is an odd number, then you will have to take floor on one side and ceiling on the other side, but that's fine. Okay, this is roughly the midpoint of the point set. And now we are at least good to go as far as the recursion is concerned. So what I will do is, okay, so what is going to be now the divide and conquer idea? Okay, so let's stick to this slide. So the divide and conquer idea would be to recurse on the left hand side Q, that is another set of points, to recurse on the right hand side R, and then do something. Yeah, of course, will not be done if we just do the recursion. But before that, let's go step by step. So first of all, remember what we decided is we will recurse on the sets Q and R. But in order to be able to do that, I will need the sets Qx, Qy, Rx, and Ry. Why? Because remember, again, I'm going to call a recursion at this on these two individual set of points, because that's how recursion works. So now the first question is, how are we going to generate these sets Qx, Qy, Rx, Ry? So one naive way is to just run the sorting algorithm again on this set of points individually. But that is too much of work, right? Because then at every level, you will need to deploy a sorting algorithm. Okay, so I don't want to do that. So can someone tell me how to generate the lists Qx, Qy, Rx, and Ry? Okay, good, Gaurav. So Gaurav is saying they're already sorted. So let's see, they are already sorted or not. Okay, so first of all, let's understand how do we generate Qx and Rx. Okay, so these two are easy. I mean, both of them are easy, but the other one is slightly, you need just one additional thing, right? So Qx and Rx are already sorted, right? Why? Because Px is sorted, right? So this you can generate by using Px. Okay, so Qx is just the first half of Px and Rx is just the second half of Rx. Okay, how about Qy and Ry? I mean, I cannot just directly copy, right? Okay, so remember the set Py is sorted according to the y coordinate, but now I have to split that set into Qy and Ry, and I want Qy and Ry to be sorted among themselves. So Qy should be sorted and Ry should be sorted. So how do we generate Qy and Ry given Py? What is the only thing that we need to do actually, in addition to the way we generated Qx and Rx? Exactly. Okay. Very good, Kushal. So what we do is we just compare the x coordinate, right? So remember we have this set Py, right? So we have this set Py and we are copying stuff into Qy and Ry. Okay. Right. Yeah, I will come to that question. So the point is, what I will do is I will pick a point from Py. Now the only thing I have to decide is whether I need to place it in Qy or Ry. This is the only thing that I need to do. And how do we do that? Well, I check the x coordinate of that point with this median point. So suppose this median point, I call the x coordinate of this median point x bar, right? So what I do is whenever I get a point in Py, I just check against x bar. I just check the x coordinate. And if it's less or equal, then I drop it here. If it's more, so this is less than or equal to x bar. If it's more, then I drop it here. But remember, because Py was sorted, I don't have to care about the ordering. This individual Qy and Ry will still maintain the relative order. Okay. Good. So there was a question, why do we need Qy and Ry? Right? So the point is, so that we will see when we do the combining step. Okay, so that's a good question, because so far we are just talking about a high level algorithm. Yeah. So the reason I wanted to generate all of qx, qi, rx, and ry is because remember we said that okay, the top level call will be on px and py. So if we want to call a recursion, then I also need similar sets for the recursive subproblems. Okay, how we will use them, of course, that needs to be seen, and that's essentially the combining step, right? Okay, so where are we so far? So now we know at least how to do the recursion. So okay, now let's talk about the high level idea of the algorithm. How will the algorithm work? So when I say recursion, what will I do? Well, suppose I'm recursing on the side q. Yeah, so I have given the sets this qx and qy to the recursive algorithm, and somehow it manages to find the closest pair of points where among the set of points in q. Yeah, because that's where I'm recursing. So suppose it gives me some set of points. So let's say these 2 points are the closest among the points that are only part of q. Okay, and let's call this distance delta q. Okay, similarly I call a recursion on the right side of the set of points, and suppose it again returns some set of point, and the distance between them is delta r. Okay, now how will I use these things to find the closest pair of points in the overall problem, in the set of points p? So remember, p is the entire set of points. So let's say by magic your recursive routines have given you delta q and delta r. Now what is the other thing that you should do in order to be able to find the closest pair of points in the entire set p? Okay, very good. So this is, again, remember, this idea is very similar to what we did when we were counting inversions. So how did we counted inversions? So remember the recursive calls, they gave us the left inversion count, the right inversion count, and then there was a third kind of inversion, which we had called the split inversion. Okay, so we count the number of split inversions. So basically here we are going to use a very similar idea. Okay, so remember delta q is the closest pair of points in the left half, delta r is the closest pair of points in the right half, but now there might be a pair of points such that one point is in the left half q and the other point is in the right half r, but they are actually closer than both delta q and delta r. Okay, so essentially what I need to do is find the closest pair of find the closest split pair in some sense. So maybe it's these two things. Okay, so here is the overall algorithm. Like whatever I have said, I have just this is just a pseudocode way of saying that. So basically, again, the base case is okay. If your set of points is only of size 2, then you do nothing. You just return the distance between them, right? There is nothing to do. If there are only 2 points in your set, uh, you don't have to care. And okay, if you are really bothered about odd and even, then when n is equal to 3, you can just apply brute force, right? You can check every pair and just return the minimum among them. So that does not cost more than a constant amount of time. Okay, so that's your base case. Now, how about the recursion? So just like we said, so delta q is going to be the closest pair on the left, delta r is going to be the closest pair on the right. And now let us define this quantity delta, which is the minimum of these two quantities. Okay, and finally, what we compute is the closest split pair, right? And closest split pair, and remember the definition of split pair, it's a pair such that one point is on the left and the other point is on the right. And suppose that I call delta S. Okay, and so after I compute this, what should I return eventually? So what should the closest pair routine return? I mean, these are simple things, but it's good to make sure that we understand everything. So what should we return now after we have computed delta S? Well, I return the minimum of the three quantities, right? So I return the minimum of delta Q, delta R, and delta S, right? Okay. Or sorry, yeah, it can be just minimum of delta and delta S. It's the same thing. Okay, there is a tiny thing that I'm hiding in this code. So this pseudocode is actually just computing the distance between the closest pair of points. It's not really returning the closest pair, right? But as you can understand, I guess, that it's very easy to kind of modify this pseudocode a little bit and actually return the closest pairs as well. Yeah, so I'm not going into that detail. So you will do an implementation of this thing in one of your homeworks. So you need to take care of those things at that point. Yeah. So this is just returning the distance between the closest pairs at every level of recursion. Any questions so far? Okay. Great. So now, okay, what are we? Yeah, Agamdeep. So we don't wait till n equals to 1. So that's the point, right? So when you reach n equals to 2, or even let's say n equals to 3, then you can just compute, using brute force. You can check every pair and just return the closest distance. So if there are 3 points, I mean, there are only, 3 choose 2. So there are only 3 options that you have to try, right? So that takes constant time. Yeah. Okay, so right. So now we are in good shape. Yeah, in the sense that, so these are my recursive calls, right? And I know that, again, if I remember the recursion that's favorite, that's our favorite one. So basically Tn equals to 2Tn half plus order n. So this is the recursion that we have learned to love if we want order n log n. Yeah. So I guess the only thing that we really need to think about is how to implement closest split pair in order n time. Okay, that is not clear, and that is going to be essentially the material for the rest of the talk, rest of the lecture. Okay, so how to do this? How to do this in order n? Okay, because if I can do that, then I'm done essentially. Then I can just write this recursion and I will get an n log n runtime. Okay, so right. Okay, so let's now get going with how to compute the closest split pair in linear time or order n time. Now, before everything else, I'm going to make an observation, which, you might find that, okay, why are we even talking about this? I mean, isn't this very obvious? Well, it seems very obvious, but you will see that this is very, very crucial. When we do the proof of correctness of this algorithm, we will notice that this observation is actually crucial in order to be able to correctly implement the closest split pair routine. And the observation is the following, that I will need to compute the closest split pair correctly if and only if they are closer than both delta Q and delta R, right? So what I mean by that is the algorithm which I'm going to give you, that will only return, or that is guaranteed to return, the correct answer for closest split pair only if the distance between those 2 points is actually less than either delta Q or delta R. If it's actually more than delta Q and delta R, then I do not guarantee that closest split pair will actually return the correct answer. But the point is that then I don't care at all, because that is not going to be a candidate solution for the closest pair of points. Okay, this is a very subtle point, but if you do not understand, then please tell me. It's a bit important to understand this thing. Okay, so in other words, I do not care. I do not care if delta is bigger than, if closest split pair is greater than delta. Yeah, I will repeat. So what I'm trying to say here is, so let's go back to this recursive picture. Okay, So remember, I have delta Q and delta R. Yeah. And all I'm trying to do now is to be able to compute the distance between the closest split pair. All I'm saying is the algorithm that I'm going to give you is guaranteed to return the correct answer if this distance that I'm showing with green is actually smaller than both delta Q and delta R. Okay. If it's bigger than delta Q and delta R, then I will not be able to guarantee that closest split pair subroutine will give me the correct answer. But I claim that then I don't care at all, because then the overall closest pair in this entire picture is not going to be this green pair. It is either going to be the white, it's going to be either of these white pairs. Okay. Is it clearer now? Yeah. And this is going to be kind of important when we do the correctness proof. Okay. So now let's now think how to implement closest split pair in linear time. Uh, so first of all, again, if I think naively, then this is not at all obvious how to do it. I mean, there are n square many points on the left hand side. There are n square many points on the right hand side. So clearly, I cannot compare each and every one of them. And remember, in the inversion counting algorithm, what saved us is that again they were just single numbers, and somehow we were able to sneak in this counting thing into our merge subroutine, and that gave us a linear time algorithm to be able to compute the split inversions. But here things are everywhere, right? They have two coordinates and whatnot. So it's not clear how to do this. But what I will aim to do, remember again, the guiding principle of these algorithms always is to be able to reduce the search space. So what I mean by search space is I don't want to cross check across every n square over 4 many possibilities. Yeah, I want to do much less. Okay. So any idea of how to reduce the search space? What could be the first idea so that at least, so I want to make a statement that, uh, it's enough to just look at these many points, not the number. I'm not asking for a number, but I'm asking for a specific set of points that I want to look at. Okay, very good. So remember, I have this median here, right? This is x bar. Okay. And what I claim now, so this is the first claim, is that it's enough actually to look at points which lie inside a thin strip. And how does the strip look like? Well, the strip looks something like this. Okay. So I draw two lines here. I did not do a very good job of drawing, but it's okay. So suppose that this is delta and this is also delta. Okay. And I claim that I only need to focus on the points which are inside this thin strip. Okay. I don't need to look at, I don't need to compare against anything else. Why is that? And remember, here again, we will be using this crucial observation that we are making. Okay. So remember, when do we really care about finding the split pair correctly? We only care about finding the split pair correctly when the distance between them is actually less than delta. Yeah. But now I claim that if the split pair, if even one point of the split pair belongs outside this strip, yeah, let's say it's this point, then the distance between the closest split pair cannot be less than delta. And that's very clear, right? Why? Because one of the points has to come from the left half. Now, if you take any point on the right half, which is beyond this boundary, then the distance have to be more than delta. Yeah. So clearly, we don't care about such pair of points. Okay. So the observation is we can, yeah, I will come to that question of delta over 2. We can only focus on points that lie in the delta strip around the median. Okay, so now there was a question, and I think some of you are also answering it. So the question is, what if I just check delta over 2? Right? Yeah. So the point is that what if one point from the pair lies exactly on the median, right? But then the other point in the pair, it might actually lie beyond this dotted line, right? Because remember, the distance can be as much as maybe a tiny bit less than delta. So it's not enough to just check delta over 2, right? Okay. Does that answer your question? Yeah. So maybe your closest pair looks like that. So yeah. So maybe the closest pair looks like this. But then if you just check in a strip of delta over 2, then you will miss this pair. Yeah. You are not going to give the correct answer. So we don't want to miss such pairs. Okay, great. Okay, so yeah, so this is the formal statement of the lemma, which says that the distance between the closest split pair is less than delta, implies that both of them will lie in S. So what is S? S is this, the set of points that lie within this delta strip. So that I call S. ठीक है, बहुत बढ़िया. So I am actually able to reduce my search space with this observation. But did we really reduce the search space in terms of asymptotic complexity? What can go wrong? No, sir. Yeah. Even I don't think we have done much here. Because in the worst case, exactly, in the worst case, what can happen is all the n-half points, so all the n-half points from the left-hand side, they might lie in this thin strip. And every point from the right-hand side, they might also lie in this thin strip. हो सकता है ऐसा? Yeah, it might happen. But then we are basically back to square one, wherever we started with. I mean, we started with this fact. We thought that, okay, we are doing something clever. We are reducing our search space, but we have landed ourselves in the same pit now. Okay, so clearly only this idea is not enough, but we will not throw it away. Okay, we will see that we can build upon this idea and we can do something even more clever. All right. Yeah, so clearly, yeah, there could be, or let's say, but all points can lie in that strip. So all points can still lie inside this strip. Okay, great. So now that brings us to the question that let's think about it a bit more closely. So the question I want to ask is, if I look at a single point, yeah, I want to be able to say that I do not really need to check the distance between this point with too many other points. This is the statement that I want to make, yeah, because that will actually reduce my search time from n square to hopefully linear time. Okay, it's not clear yet how to do that, but the hope is basically that for a given point P, we should not need to check against too many other points. Okay, but we will see how to do that. So let's say I fix a point P. So, okay, now let's do it like this. So suppose PQ is the closest split pair such that the distance is actually less than delta. Okay, so remember, this is the case that we are concerned about. If they are bigger than delta, then I don't care. So suppose that this closest split pair, it's PQ, and the distance between them is actually less than delta, right? So now I will draw a picture which is actually going to be the workhorse of why this actually works, or why we can make this work. So suppose now that P is the point which has the smaller y coordinate between P and Q. Okay, so P and Q are the 2 points. So P is the point which lies below Q in this picture. Yeah, okay, right. So now, and remember, both of them have to lie inside this thin strip S, because that's where I'm going to restrict my search space. I'm not going to go beyond that. Okay. So now we are actually going to do a thought experiment. Okay, this is not an algorithm yet. So we will see how this leads to an algorithm. So let's just do a thought experiment. So imagine I place a grid onto this picture. Okay, what is a grid? So grid is a picture which looks like that. Okay, right? So imagine I place a grid on this picture, but the grid will have 2 properties. The first property is that one of the grid lines will coincide exactly with the median. So this is the X bar line, remember? So I have the set Q here and I have the set R here. So one of the grid lines, I will make it coincide with exactly this median point. Yeah. And each side of the grid, I take to be delta over 2. Okay. The third point is one of the grid lines, I actually coincide with the y coordinate of P. So it's going to be something like that. Okay, so I'm just drawing a grid like this. So suppose, yeah. So it looks something like that. Shit. Okay, and each side of this grid is of size delta over 2. Okay, so imagine this is a square grid. Okay, I'm drawing it in a very weird way, but this is a square grid, right? So again, I'm just doing a thought experiment here. So I'm putting a grid on the top of this picture. Each side of the grid is of size delta over 2, is of length delta over 2, and there are 2 other things that I'm ensuring. The first thing is one of the grid lines coincide with the median point X bar, and another grid line that coincides with the y coordinate of the lower point P among this closest pair. Okay, so let's actually draw the median line with a different color so that this picture is a bit more clear. Suppose that. Okay. So any questions about this picture? Why, where this picture came from, and etc. Okay. 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 So now remember, the moment I place this grid in my mind, it gives me these boxes. Okay. And P lies in sort of this corner box. For example, suppose P lies in this corner box. The question I'm going to ask is, where all can the point Q lie? Okay, which are the boxes where the point Q lies? So let's just go one by one of where all can Q actually lie. Okay, so can Q lie here? Well, it can lie here, but remember I'm talking about split pairs, right? I'm only talking about split pairs, so I really don't care about I mean, even if Q lie here, that is not something it bothers me, right? Because remember, it's a split pair, so Q it should actually be on the other side of the median. So Q cannot lie here. Okay, can it lie here? Yeah, definitely. Definitely it can lie here. Why not? Okay, can it lie here? Right? Okay, no, it cannot lie in the third box. Why can't it lie in the third box? Because then the distance between P and this point might actually exceed. Well, if you think about it, that's not completely true. What can happen is that yeah, it's correct. It cannot actually lie in this box. Yeah, because if it lies in this box, then the distance between the point P and the point Q, that is going to be more than delta. Yeah, because each side of this box is delta over 2. So clearly, if Q lies in this box, then okay. So in which case, Ananya? Oh, no, no, no. Sure, sure. I'm just talking about this particular picture. Yeah, you are right. You are right. You are right. If P lies here, then of course, yeah. Actually, yeah, I was wrong. Yeah, I take it back. Actually, Q can lie here. So suppose the point P is actually here, right? So suppose the point P is here, then the point Q can clearly lie in this point, in this box. Okay, so this can happen. Okay, so similarly, let's just check some other boxes. Okay, now x coordinate we understand. So in terms of x coordinates, this point Q cannot really lie beyond this box. So that we are more or less convinced about. What about the row? What about if we go, along the rows of this grid? Okay, so can the point Q, for example, lie in this box? Yeah, it's essentially the same argument, right? Because then the distance between P and Q will become more than delta. So essentially the take home message is the following, that if there are two closest pairs, right, then both these points have to lie in the first two rows of this grid. When I say first two rows, I mean that the bottom line of this grid is actually coinciding with P. Yeah. And then if I just look at the two adjacent rows, then whatever the point Q is, it cannot lie beyond these, let's say, 8 boxes. Okay. You can make it 5, 6, whatever. I am not really bothered about, optimizing those small constants, but clearly the point P and Q cannot lie beyond these 8 boxes. Okay. That is the take home message. Okay. So let's see. There have been some discussions. Oh my God, that's too much. P could lie closer to the median. Yes, that we have resolved. Always greater than equals to delta. What does that mean? Okay. Yeah. So everyone understands what I'm trying to say here. Yeah. So all the pair of points. Yeah, I mean, if there is a pair of point which is closer than delta with each other, then both of them have to lie in one of these 8 boxes. Okay. So now what does this tell us? Well, what this tells us is that now I can only focus on these 8 boxes. It can lie in the top square. You mean this one? Well, if the grid line coincides with, if the bottom of the grid coincides with P, then I don't think this can happen, Gaurav, because then it will be more than delta, right? So I'm assuming that the bottom line of the grid that I'm drawing, that coincides with the y coordinate of P. But then if it goes to the third box, or to the third row, then the distance is more than delta, right? Each is delta. No, what do you mean? The y coordinate would be more than delta, right? See, the bottom line of this grid coincides with P. So now you have to traverse delta half and delta half. So if you are in the third box, then if you are in the third row, then you will exceed delta, right? Or am I missing something? So this is important to understand. I am not placing the P to be on the line in the top right corner of this box. Top right corner of which box are you talking about? Let me give some names. So let me say, call this box, let's say, I don't know, Z. So are you talking about the box Z? Then which one? Yeah, so the box in which P is lying. No, but all I'm saying is, do we need to check beyond these boxes, beyond these two rows? Is the question that I'm asking. That we don't have to do, right? Yeah. Okay. No, Gaurav. So I think you can. Okay. So Gaurav, let's take this after the class. I think what you are missing here is that I'm placing the I'm placing the grid line, coinciding with P. But maybe I'm missing something here. Yeah, you might be correct. Okay. Okay. So let's go ahead. So what we realized is that, okay, whatever are the closest pair, so the hunt for closest pair has to be only restricted into this into these 8 boxes, let's say. Okay. Remember, I'm not yet talking about any algorithm. We are not yet, we don't know how to do this, how to, shall we draw a grid or what? I mean, this looks very complicated. Okay. But we'll get there. But all we have decided here is, देखो, हम search space को reduce कर रहे हैं. First, we said that we will just look at this thin strip. And now what we said is, if I fix any particular point, then I only need to be able to check this point with, only need to check this point P with those points which lie in one of these 8 boxes. Okay, not in this one. So let me actually erase this thing. Okay, only these 8 boxes which I have shaded, right? But are we done yet? Or what could be a potential problem? Right? Yeah. So have we really reduced our search space now? So observation 1 is, it is enough to look at 8 boxes for any fixed point P. Any fixed point P. Okay. So all we have realized so far is, okay, for a fixed point P, I have to check these boxes. But then these boxes might contain all the points. What if these boxes contain a lot of points? These boxes might contain, let's say, theta of n points, let's say n half points. Every point might actually lie in these 8 boxes. Yeah, for a specific, for, I don't know. I mean, they could be very densely packed, right? But can that happen? Yeah. Okay. So my claim is that every box will not contain too many points. In particular, none of the boxes can actually contain more than 1 point. Why is that? Why do I say that no box can actually contain more than 1 point in this picture? Exactly. Okay. So remember, so first of all, there are two things that we need to check here, right? First of all, remember that the way I have placed my grid, so remember, this is why it's important to place a grid line along the median line X bar. Now, this automatically tells me that none of the boxes can actually cross the median line. They will either be completely on the left or completely on the right. It's obvious from the picture, but when you write the proofs, you have to think about these things carefully. Okay, and this is where we are using the idea that the grid box in our thought experiment we have placed coinciding with the grid line. Okay, so a box either lies entirely in Q or it lies entirely in R. Yeah, a box cannot look like that. ऐसा नहीं हो सकता. Good. So now suppose, for contradiction, that two points actually lie inside a single box. Okay, so suppose ऐसा कुछ है. Suppose 2 points lie inside a single box. But then what could be the maximum distance between these points? Well, the maximum distance is the diagonal of this square. And what is the diagonal? What is the length of the diagonal of this square? Well, the length of diagonal of this square is delta over square root 2. okay, which is less than delta. But I know that delta is the minimum of delta Q and delta R. So this is clearly a contradiction. So any 2 points which completely lie inside R, they cannot have a distance which is delta over square root 2 between them, which means that 2 points cannot lie in this square. Okay. So now we are in good shape. Why are we in good shape? Because now suppose, so what I will do is, let's say I'm checking against a point P. Now, how many points do I really need to check against? Well, it's clear that I just need to check against 8 different points. Yeah, because I only need to focus on 8 boxes. Maybe 8 is an overestimate, maybe 6 works. It's up to you to figure it out. But okay, I'm happy with 8. Okay, so actually it's 7, right? Because P itself has to be in one of the boxes. So it's enough to check against 7 boxes, right? And each box has only 1 point. So it's enough to just check it against those points. But how will I know which of these 7 points are? I know there are 7 points. Why can't there be 2 points in one box? Good. So let's go over this proof once again. So Samiksha, suppose there are 2 points in the same box. So the first observation that we are making is that any box will completely lie either on the R side or on the Q side. That is either on the right side of the median line or on the left side of the median line. This is the way that we have imagined our grid. Okay. Now, if that is the case, then what is the maximum distance between these 2 points? The maximum distance these 2 points could be delta over square root 2, right? Because it's the diagonal of this square. That could be the maximum distance. But I know that the minimum distance between any pair of points on the R side can be at least delta, right? That is the definition of delta. Because remember, delta tak hum kaise pahunche the? We were recursing on Q, we were recursing on R, and delta is the minimum of these 2 quantity. Okay. Right. Okay, there is another question. Aren't there only 4 points to be checked in other? Right. That's a very good point. Yes. So it is indeed the case that we should need to only check these 4 boxes. That's a very good point. Okay, here is the question. So somebody is asking that why do we need to check all these 8 boxes or all these 7 boxes? It's actually enough to focus on the right hand side of the median line, because that's where the split pair is going to happen for P. But the point is that, so this is actually what I was trying to sort of get to, that so far we have understood that we have to check against 7 different points. But how do we know which are those 7 points? Are we going to draw the boxes? Are we going to check whether these points lie in the boxes or not? We are not going to do that. Okay, so how are we going to check against these 7 points? How do we know which 7 points I need to compare against for P? Exactly. So here is where I think there was a question right at the beginning of the lecture. Why do we need this sorted list QY and RY? So this is the answer to that question. Now we are going to use those lists. Okay. So suppose that SY is the sorted list. So S is all the points that are lying in this thin strip, and SY is the sorted list. So don't worry, this slide is becoming a mess, but I will write everything clearly in a few more slides. Okay, but suppose SY is the set of points sorted according to the Y coordinate. Okay, and now I am just doing a scan along this list, and somehow I am at this point P. Okay. So now all I need to do is check the next 7 points in this order. And why is that enough? Well, because I know that every time I advance my pointer, I am actually going to hit one box. So abhi main P par hu. Suppose, in the worst case, P is in the left corner box. So if I advance my pointer in this SY list, then I will hit a new box. Again, if I advance my pointer, I will hit another new box. Yeah. But the moment I reach this boundary, then I know that I will actually shift to the next row. Why is that? Because remember, I'm only focusing on the point set S. I'm not going beyond that. So I've restricted my X coordinates only inside this narrow strip, which I call S. Okay. So if I just take the sorted order and I check P against the next 7 points, then that is enough for me. I don't have to go beyond that. And I think this also answers the question that why isn't it enough to check for the right 4 or whatever? Yeah, because then we have to keep more information that which of these are on the right or which of these are on the left. Why not just take the points in the right side? Yeah, so that's what I'm saying. But the point is, this is only for this picture, right? But maybe, there is a point which is on the left hand side, on the right hand side. P is on the right hand side, but then you have to check. Is that correct? Yeah, I think actually you need to, yeah, or you need to keep some more information, right? Okay. Could I repeat again? Which part do you want me to repeat? Yeah, I can repeat everything again, but so Naval, which part? So why, you mean how do we find these 7 points? That part? Yeah, okay. So why not right hand side? So the point is, no, I'm not saying it's wrong if you take the right hand side. All I'm saying is then you have to keep an additional information of which points are on the right hand side with respect to every point. But that was, but that's too much information, right? How do you know which are on the right hand side? This is a thought experiment that you are doing. But imagine your algorithm. Your algorithm does not know what is on the right or what is on the left. Okay. Yeah. So SY is the set of points in this thin strip with their Y coordinates sorted. So this is a list that we are deriving from the set QY. Okay. Ayushi, that's very important to understand. No, we are not making the grid as part of the code. All we are doing is for every point, we are checking the next 7 points in the sorted order capital SY. Okay, that is your algorithm. So you do a linear scan over the list SY, which is the set S sorted according to your Y coordinates. And for every point, you are just checking it against the next 7 points. That is all you are doing. Yes, yes, exactly. So the next 7 sorted points in the array Y. Yeah. So that is the beauty of all this. So this is all in your mind. This is just for the correctness proof. You don't need grids and everything in order to implement. Okay. Any more questions? Yeah, Yuvraj, I'm not saying you cannot check the right hand side, but all I'm saying is that how do you know what is the right hand side? What is right hand side really? I mean, this is just with respect to this particular picture, right? But this point P can be anywhere. Okay. So just think about it. If you don't understand, we can take it offline again. Okay, good. So Ananya is asking, how do we know the next 7 points will cover all the 8 grids? So let's see. Let's see why is that the case? So Ananya, think about it like this. So let's say P is the left bottom corner. P lies in the left bottom corner grid. Okay. The point is, what we just argued is that every grid has exactly 1 point. Okay. So the point is that the moment you have another point, you have to so in your mind you have to think it like that. The moment you are going to the next point, you are changing grid. Okay. So suppose P lies in the left bottom corner. So you let's say advanced your pointer by 1. Okay. So which grid are you going to get? At least you have to shift 1 grid, right? Because every grid has 1 point. This next point, which is lying next to P in this sorted order SY, that cannot lie in exactly the same box. It has to lie at least has to lie in the next box. So the moment you are advancing your pointer along this list SY, every time you advance your pointer, in this picture, you are actually changing a box. Okay. So that is the whole point. But I know that okay, after 8 boxes, you are going to go out of this picture, right? So after you have traversed, let's say 7 boxes from P, you are going to get out of these 8 boxes. So then you don't need to check any further. Okay. How do we know that 8 traversals are in our desired boxes? Okay. So again, I mean, this SY set that is sorted according to your that is sorted according to your Y coordinates. Okay. So what can happen? The moment you change, the moment you go from one point to the next one. So let's say again, you start, I'm saying that you are starting at a specific point P, right? So the moment you change a box, the moment you change the pointer along this list SY, you are going to change, you are going to go to the next box, right? Okay. Yeah. Okay, so it's also possible that we end up checking 7 points on the same half. That is absolutely possible. That's a very good point, Naval. Yes, it can very well be, well, not 7, right? Left half में कितने boxes हो सकते हैं? Soham, I will come to your question in a moment. Naval, I'm asking you, अगर मैं सिर्फ left half में same half में हूँ, yeah, there could be only 5 cases, right? Or maybe 4 cases actually. So only these 4 boxes, right? So that means that these other 4 boxes on the right hand side, they are empty essentially. Yeah, yeah, exactly. Yeah, but the point is that, yeah, right. But we don't care about those pairs. So essentially you can ignore those pairs. You only care about the pairs which are split, right? Which are on the 2 sides. Okay, so Soham has asked a question. He's asking that why aren't we checking P with the points that have lower Y coordinates? So how should we answer that question? So यहाँ पर मैं बोल रहा हूँ कि you just advance your pointer. Right, because remember, I am doing a linear scan. I am starting from the beginning of SY. So whatever points have lower Y coordinate than P, those have already been checked with P because you are moving from left to right along this array. Okay. Okay. Okay, let's now write it. Let's now write it. Okay, so yeah, this is like this is the essentially the lemma that we proved that suppose AB is the closest split pair and they are actually closer than delta, and if A appears before B in this list SY, then B can be at most 7 positions away from A in that list. So this is all that we have proved. Okay. And now this essentially gives me the closest split pair algorithm. So all I need to do is I need to traverse the array SY, which is sorted according to my Y coordinate. And for every point I just need to check for the next 7 points. That is all I need to do. Okay. And whatever is the minimum, I return that. If that is less than delta, then I return that from the recursive call, or not the recursive call, you know, the high level call. Otherwise, yeah, delta is really the minimum. Okay. And now this is clearly, okay, this algo is wrong. Why is this algo wrong? Yeah, it might be wrong. Why? Oh, I see. I see your point. I see your point. Oh, okay. You are absolutely right. Yeah. Sorry. I see your point. So, okay. So I'm checking with this point, but what if, you know, the closest pair lies somewhere here? That is what you are saying, right? Yeah. You are right. Okay. ठीक है. I take it back. Not -7. Yeah. Because I might miss checking the last few pairs. You are right, Gaurav. Yes. So yeah, let's just check with up to mod sy. Doesn't hurt, but we have to keep a check that whether they're overflowing. Yeah, so these are the implementational issues that you have to keep in mind, which is why you will implement this algorithm as part of your homework. Okay, that's a heads up. Okay, yeah, so what I'm showing you is a very high level idea of that algorithm, but clearly you need to do this minor checks and find the median and do stuff. Okay, but that is the overall algorithm. So any questions? Is there any non-recursive solution to this problem? Gaurav, not that I know of. I think this is like this is a classical it's a classical divide and conquer thing. So I don't know if yeah. Yeah. Yeah, I mean, in some sense, that's more of an implementational thing. I mean, any recursive algorithm you can probably convert to an iterative algorithm, but the underlying principle is still divide and conquer. Yeah. Okay. Right. Okay. Any more questions? So we can discuss now if something is unclear. Yeah, homework is in pair. That has been announced, right? That's why you have made your pairs. Okay. So I wanted to show you another proof, but I don't think I have time to do that. So another proof of this same fact. But yeah, but let's keep it. I don't think we have enough time to do that.